This is the Academy for Allied Health. Mr. Smith, we are in physics. We've been dealing with circular motion. A lot of this is for movement of planets, but a lot of this also comes into health concerns. You have to understand this kind of movement and angular velocities. It'll really come in handy as you try to understand. Anyone who gets into biomedicine wants to start designing things to help keep people from hurting themselves in auto accidents or even dealing with artificial limbs, etc. You've got to understand some of this basics. Okay, we were looking at, and we've looked at already the idea of circular motion. We've looked at gravity. Now we're going to look at just the rotational mechanics itself, okay, and simple machines. This is rotational mechanics. We'll do simple machines in the next video. So remember, spinning objects rotate about its center of mass, or its axis. That's what we've said, right? Okay, so there's a couple of types of motion. Translational motion is here to there motion. That's linear. Object's entire mass can be assumed to be at its center of mass. The object is considered to be a point mass. Rotational motion, on the other hand, is spinning, as we've talked about before. Remember, when you rotate, you spin. When you revolve, that goes then around some other center. But rotational motion is spinning. So the object must be considered to be an extended mass if the rotation is crucial to the motion, such as a boomerang. In translational motion, an object's resistance to changing its state of motion is called inertia. The greater the mass, the greater the inertia. Okay. In rotational motion, object's resistance to change is called its moment of inertia, which is a capital I. Also called rotational inertia, the more mass that is farther from the axis of rotation, the greater the moment of inertia. Okay, both of these deal with rotational inertia and the moment of inertia. Like valenda. I never get that right. All right, the moment of inertia values have been tabulated for simple shapes. That is, for a solid sphere spinning about its central axis, it is 2/5 mr squared. M is the mass, r is the radius. Other shapes for which moment of inertia is easily found are a point mass revolving at radius r, which is I mr squared. A hollow sphere rotating about its axis, I 2/3 mr squared. And a thin disk rotating about its axis, like a CD, 1/2 mr squared. Okay? Torque. Torque is involving twisting and rotating. Okay. Now, torque, that's the symbol for torque. Torque looks like work, doesn't it? It is. It's rotational, though. Force times distance. Torque, applied force, distance between the force and its pivot point, or its center point, or what it's revolving around. That's the key you've always got to understand. So that means force and distance must be parallel to each other. Or, I'm sorry, it's not parallel. The force and distance has to be perpendicular to each other. You must be applying the force perpendicular. We'll see how this works. Okay, like spinning a wheel. You're applying the force, but it's perpendicular to the distance. You're applying it around the center of the wheel. Okay, let's try one. When a 62 Newton force is applied to the end of a wrench, force makes 129-degree angle with the handle. Distance between the force and the bolt is 39 centimeters. What is the torque? Okay, again, force times distance. Of course, you've got to resolve so that you get a true perpendicular. So use cosine 39. right? Why? You only need the perpendicular component, remember? And your answer is 19 Newton meters. That's the force being applied, or it's a torque being applied. That's torque. Okay? There is something called static equilibrium. We've dealt with equilibrium. Remember, we dealt with that in chemistry. Now we've got it here in physics, where forces are acting on an object are balanced and the torques acting on the object are balanced. So it's not enough to just have balanced forces. The torques have to be balanced. Okay, that's not an equilibrium. But if the forces are at the center, now you have equilibrium. Torque is 0. In the first example, torque is not 0. Their balanced forces, they're the same, but what's going to happen? It's going to rotate about the center. Okay? Let's try an example. A 4-meter horizontal beam is supported at ends. We're going to have a point load of 1,000 newtons acting perpendicular at the beam's center. Find the support reactions. What does that mean? Well, support reactions, equal and opposite, right? Third law. Remember, third law is always acting here. So in order for those two supports to keep the beam from falling, they have to react against the force acting at the center. So here's your force at the center. It's directly in half. Okay? So what you want is, you want the torque at A and B. Those reactions. That's what R is. They're reactions. That means each one is 2 meters. You only have to figure this out once. The sum of the forces is going to be 0. Okay? So therefore, the reaction forces at some of the reaction forces minus 1,000 must be 0, which means they've got to add up to 1,000, which of course will work. So the sum of the torque on 0 has to be, sum of the torque on A has to be 0. So you get RB times 4 minus 1,000 times 2 has to equal 0. Okay? So each one has to. You can solve these any way you want. If you solve for RB, you would get 500 newtons. Remember, sum of forces have to equal 0. Therefore, RA is 500 newtons. You could have worked this out where you were doing the sum of the torque on B. And it was RA 4 minus 1,000 times 2. You're going to get the same answer. Okay? Take a look at this and make sure you understand that. All right. Now our beam is supported at its ends. The point load is going to be 3.2 meters from the left. Again, what are going to be the support reactions? Okay? Same idea, same situation. I don't have it at dead center now, so now I have it a little bit different. So it's 3.2 meters from RA, and it's only, what, 0.8 meters from RB. So again, same situation. Sum of the forces is going to be 0. We will look at the torque on A, which is 0. That's just convention. That's how it goes. So that means that minus the 1,000, 3.2 is going to be 0. Okay. Notice they're in opposite directions. Therefore, they're subtracted from each other. They still have to equal 0. So we solve for RB. We get 800. And that means RA is 200. Okay, simple. Now we're going to try a 12-meter horizontal beam, again supported at ends. Center point loads, or actually, perpendicular loads of 300, 400, and 500 newtons, acting at 3 meter, 5 meter, and 7 meter respectively from the left. Find the support reactions. Okay, so let's see what we're dealing with. There we are. Well, what does that mean respectively? Notice the 300 is at 3, 400 is at 5, 500 is at 7. You want the support reactions. It's easy to do. Okay, those are all your distances. You add your forces, you get 0. 3 and 4 is 7. 7 and 2 is 1,200. You get 1,200 newtons acting against RA and RB, but the beam is up. It's supported. So that means you can tolerate, right? This is how you have to work things out for bridges. So RB at 12, which is all the way at the distance. Remember, it's going to react, and RB's reaction will affect RA. So you've got the 300 at 3 minus the 400 at 5 minus the 500 at 7. All of that's got to equal 0. Okay? Solving for RB gives you 533 newtons. Okay, then going for what A is, it's 667. Simple. Setting up two equations. We all know that all the forces are 0. Why? Because it's not moving. The beam is being supported. Okay? Again, let's try to find some support reactions. We're not going to deal with the beam's mass. Here you're given them. Now the supports are inward a little bit. Okay, so this is a little bit different. All right, our sums are 0. Again, you add up all those masses acting opposite to our supports, and it still has to equal 0. So let's find torque around A. We know it's going to be 0. Now you got a couple different ones. RB is 7 meters away. Then there's the 850, that's 13 meters away, 6 plus the 7. Then there's the 210, that has to get figured in there. That's 3 meters away, and that's plus. Notice because it's going in a different direction, you add it instead of subtract it. It's not pushing on A, or it's not operating on A in the same way as the 850 is. You don't have to worry about the 630 because it's directly opposite RA. So it's not really doing anything for torque. Okay, so we solve for this. You get 1,490 newtons for RB. And of course, going into the original problem being that the sum is 0, you get an RA of 200 newtons. Okay. Right, now we're going to use a 14-meter horizontal beam supported at 4 meters and 12 from the left. Again, point loads of 510, 930, all downward. Act 2 meters and 9 meters respectively from the left. The beam's weight acts as a uniformly distributed load of 75 newtons per meter along the entire beam. Now we find the support. Okay, now we're going to use the beam's mass. We haven't had to worry about beam's mass before. Now we're going to deal with it. Okay, so let's deal with this. To deal with the distributed load, concentrate the distributed load, make it a point load. Make it at the center of the span. So 75 newtons per meter times 14 meters, which is the length, 1,050 newtons. That point load acts at the center of the span. So it's at 7 meters. And it has to be included in your reaction. Or, I'm sorry, in your equation, in your calculations. Okay, so sum of forces is 0. We know all the forces up that are being pressed downward on the beam are 2490. We know that the two supports support that. So they'll also add up to 2490. Everything is going to equal 0. Again, torque around A has to be 0. Therefore, the reaction of B at 8 is 8 meters away, minus the 930 at 5, minus the 1050 now at 3. Okay? How do I do that? You figure it all out. Figure out where the center is, which is 7. right? 2, 4, that means it's 3 meters away from A. Plus, since the 510 is acting in the opposite direction of the other two, it's added, and it's 2 meters away. All of that's got to equal 0 because torque is 0. You get an RB of 850 newtons. You get an RA of 1640 newtons. All right? Good. Newton's second law for rotation. Okay, remember, sum of all forces, mass times acceleration. That means the sum of all torques is the moment of inertia times the rotational acceleration. Right? Sum of torques, moment of inertia, angular acceleration. In rads per second squared. So a football player applies a net torque of 0.082 Newton meters to a football having a moment of inertia of 5.7 times 10 to the minus 4 kilogram meters squared. If it starts from rest, what is the angular acceleration of the ball over the time the quarterback takes to throw it? Okay? Remember, sum of the torques. So we can change that around so that sum of the torques divided by the moment of inertia is the angular acceleration. Okay? Simple. We don't even need time. I've been given a net torque. It's 0.082. You get 140 rads per second squared. Divide that by 2 pi radians or 6.28, and you can come up with how much spin it really has, how many times it'll revolve. Now let's try a compact disc. Compact disc with a mass of 8 grams, radius of 6 centimeters. Starting from rest, the CD speeds up to 220 RPMs at 1.6 seconds. What's the torque by the CD player? What's a CD player? That's going to be coming like a turntable. What's a turntable? Right? Okay. Remember, some of our torques, moment of inertia, angular acceleration. What's our moment of inertia? Okay. Well, remember, go up to one of the first slides. It's 1/2 mr squared. So don't forget to change the grams to kilograms and the centimeters to meters. And you get 1.44 times 10 to the minus 5 kilogram meters squared. Remember, angular acceleration is angular velocity divided by the time. Initial angular velocity is, of course, 0. To find the second one, the final one, it's 220 revolutions per minute, RPM. So convert that. 1 minute is 60 seconds. And of course, a revolution is 2 pi radians. And you then get 23 radians per second. Okay, you can feed that in. So now you got the 1.44 times 10 to the minus 5, which is your moment of inertia. Take your angular velocity, divide it by your time. You will come up with 2.1 times 10 to the minus 4 Newton meters for torque. Now, a little talk about angular momentum. Linear momentum is mass times volume. Angular momentum is similar, only its moment of inertia, or I'm sorry, not mass times volume. Listen to me. Right? That's dealing with density, and that's not density properly either. It's mass over volume. No. Angular momentum is the moment of inertia times the angular velocity. Momentum is mass times velocity. So L is angular momentum. I is moment of inertia, of course. And we have the angular velocity, which is our weird little W. Angular momentum, therefore, is in kilogram meters squares per second. So, if the mass of the Earth is 6 times 10 to the 24 kilograms. Its mean radius is 6.4 times 10 to the 6 meters. Find the angular momentum of the Earth as it spins on its axis. So, we use for a sphere 2/5 mr squared. Okay, feed in our numbers. We get a moment of inertia of 9.83 times 10 to the 37th power kilogram meters squared. Okay, our angular velocity is, of course, 2 pi rads at 24 hours, which we then reduce to radians per second, which will work out to 7.27 times 10 to the minus 5 radians per second. We then feed that into our angular momentum equation, and we get 7.1 times 10 to the 33 kilogram meters squared per second. Pretty big. Which we would expect. It's the Earth. It's massive. We should have a massive angular momentum. All right, next, a 68 kilogram man is sitting on a 3.2 meter, or is sitting 3.2 meters from the axis of a spinning wooden plank with a mass of 95 kilograms and a length of 7.8 meters. The axis goes through the center of the plank, which spins at 1.3 radians per second. Let's find the angular momentum. Okay, so here's our guy. I hope he doesn't get hit in the head. He's 3.2 meters away from the axis. It's spinning. It's 95 meters. Its length, or it's 95 kilos. Its length is 7.8 meters. The rotation is 1.3 radians per second. That's the angular velocity. We need angular momentum. So how do we find moment of inertia? Okay, moment of inertia for a plank is 1/12 ml squared. That's L, lowercase l for length. Okay, that's for a plank. Plus, we have the man, who's mr squared. Okay, remember, a man is always a point mass. So we get 482 plus 696. And that gives us 1178 kilogram meters squared for a moment of inertia. Then we feed that in. We've already got the angular velocity, which is 1.3 radians per second. Feed in our two pieces. And we get 1.5 times 10 to the third kilogram meters squared per second. Now, we've got to talk about the law of conservation of momentum. When the net external torque acting on a system is 0, then angular momentum for the system is conserved. Okay, that means final angular momentum equals initial angular momentum. And of course, that means our equations equal each other. That happens with ice skating, and it certainly happens with a diver. Okay, so let's talk about a merry-go-round ride. The merry-go-round has a mass of 115 kilos, a radius of 2 meters. It's spinning at 2.6 radians per second. A 65 kilogram student is standing on the edge. Find the new angular speed or velocity after the student is moved to a distance of 0.5 meters from the axis. So the student's going to move in 1.5 meters. Okay, remember, angular momentum is conserved, so they're going to equal each other. We've just got to change the new angular velocity. The moment of inertias are going to be the same. Okay, we want the moment of inertia for the merry-go-round plus the student times the initial angular velocity. That means for the merry-go-round, it's 1/2 mr squared. For a person, it's simply mr squared. Feed those in. Of course, it's 2.6 rads. We get a moment of inertia initial of 1274 kilogram meters squared per second. Okay, we're flipping around. Now to find the final, we don't have the final angular velocity, but we do have what our change is going to be, which is the radius is 2 meters, so we still have 1/2 mr squared for the merry-go-round, but now the person is at 0.5 meters. That's his radius. So we figure that in. We get a moment of inertia of 246.25, which we can then use to find the final velocity. Remember, they equal each other. It's conservation of angular momentum. And that final velocity will be 5.2 radians per second. Velocity increases. All right, now rotational kinetic energy. Let's take a look at that. Remember, kinetic energy is 1/2 mv squared. When it's rotating, it's 1/2 moment of inertia times the angular velocity squared, where Ke rot is rotational kinetic energy. I, of course, is a moment of inertia, and we have angular velocity in radians per second. Kinetic energy is still in joules, even though it's rotational kinetic energy. So let's look at the Earth's rotational kinetic energy. It has a mass of 6 times 10 to the 24 kilos. Its mean radius is 6.4 times 10 to the 6 meters. That means at the equator, what is its rotational kinetic energy as it spins? Okay? Remember, we've already gotten previously its moment of inertia and its angular velocity. So let's feed that in. 1/2 IW squared. Feed in our numbers. We get a kinetic energy of 2.6 times 10 to the 29th power joules. That's it. Thanks very much. We'll go over these and we'll do some problems of them in class. See you then.